Okay, here's another rational function. We have a quadratic divided by another quadratic, so we better first factor this before we try to sketch its main characteristics in the graph paper in front of us here. So f of x, if we factor the top, it's going to give us x minus 3 multiplied by x minus 1. And the denominator, we get an x minus 3 multiplied by an x minus 2. And right away we can see that we can divide x minus 3 into x minus 3. That factor is gone, or it's been removed, and that removed factor is going to create a point of discontinuity. So that will be a point of discontinuity on our graph. So our simplified rational function, this is very similar, of course, a form that we're pretty used to and we've seen in previous examples, just a linear over a linear, but please remember you have to keep the domain restriction of that point of discontinuity, even in the simplified function. Okay, so we have I guess a more typical situation now. So let's maybe put our asymptotes on the graph paper in front of us. So remember the horizontal asymptote for either, I guess, the simplified version or the original, whatever you happen to be looking at, you'd be taking a ratio of the x coefficients, or they should say the highest power x coefficients. So if you're looking at the simplified function, that'll be 1 over 1. And if you happen to look way up in the original, if you want to take the x coefficients again of the highest powers of x, of course you're going to figure out the same location of your horizontal asymptote, still going to be y equals 1. And we have a vertical asymptote in our simplified function here. Of course, that's going to be where division by 0 happens, and that's going to be what makes x minus 2 equal to 0. So of course that's going to be x equals positive 2. So it better be clear that we have two domain restrictions on this function. The one that you're most likely going to miss, though, is the point of discontinuity domain restriction, which is why I focused on that first. Okay, so let's sketch our vertical asymptote and our horizontal asymptote. Okay, so there we got two key pieces to our rational function. And I think we should add our intercepts as well, because that's pretty easy to do. If I evaluate, again, my simplified function is easiest to work with. If I sub in x equals 0, in that function we'll get 0 minus 1 over 0 minus 2, which tells us our y-intercept should be at positive a half, which we'll put right there. And if we're looking for our x-intercept, remember we have to look at the top of our rational function. So if we look at this and try to figure out what makes our numerator equal to 0, then that looks like that's going to be x equals 1. So I guess I'll put it there in green. So I think that should be enough to go on. There's one branch of our rational function. And the last feature, of course, we have to include here is that point of discontinuity. And remember, that occurred at x equals 3, that removable factor of x minus 3. So if we evaluate this function, now remember this is undefined, so I better watch my notation here. I better not actually show that I'm trying to evaluate it. I'm trying to find the hole that's in this function, so I'm just going to substitute x equals 3, and then I'm going to get 3 minus 1 on the top and 3 minus 2 on the bottom, which is going to give us 2 over 1. So this is the location of our point of discontinuity, because remember f of 3 is still undefined, which is why we're going to put an open circle here at x equals 3, and the y value that it almost wants to have, remember, is going to occur right there. So that should be enough to go on. We can sketch our second branch. Okay, so there it is. We got a graph, I guess, not just a sketch. That's decent enough, I think, to call a graph. We got our asymptotes, we got our intercepts, and we have our point of discontinuity, which I will label here just to be 100% clear, and that occurs at 3 and 2. Okay, so let's finish off by looking at some limits. And of course, use our graph to help guide us here. So, and it'll be a summary of all the limit work that we've done to date. So I think first and foremost, the limit of this function as x approaches that point of discontinuity location, which of course is located at 3. So remember, the limit of a function at a point of discontinuity, if we need a refresher course, notice as x approaches 3 from the left or the right, we can see those arrows coming together right at that point in space, and that tells us our limit exists. And I better write the correct value, not 3 of course, but 2, and that is the y value of that point of discontinuity. And remember, all that limit is saying, if the limit exists, as x gets closer to 3 from either side, that y value is inevitably going to get closer and closer to 2. So that's our point of discontinuity limit. What else can we do? We maybe should look at our horizontal asymptote limit, and we'll do those in yellow. And remember, that is involving x approaching infinity. We can x can approach negative infinity, and x can approach positive infinity. So if x gets far, far left, of course, this function is going to get closer and closer to that horizontal asymptote from underneath, which of course is located at 1, and the same thing if x goes far, far right. So those are the two limits involving our horizontal asymptote, and sometimes we refer to that as end behavior. So when x gets far left or far right, the horizontal line is the predominant factor, I guess, feature with this function. So what else do we have left? We have our vertical asymptotes. So remember, if we're going to try to describe their behavior of our function around that vertical asymptote, of course that happens at x equals positive 2. So we have to look at the behavior of that function as x approaches 2 from the left and as x approaches 2 from the right. So if x approaches 2 from the left, we'll do this one first. We can see our function y values are getting smaller and smaller and smaller. So that means our function is zooming off the graph paper towards a negative infinity. And similarly, if x approaches 2 from the right-hand side, we can see our function is skyrocketing off the graph paper. Okay, and one last little add-on here. It's important to know that if x does approach 2, from both sides on this function, we have to say that this limit does not exist. And if that's confusing, think back to the first limit here where x approaches 3. In order for a limit to exist, the arrows have to come together at a specific point in space, which of course will have a y value that's a real number. And if we look at x approaching 2 from the left or the right, there's no arrows coming together. It's just kind of that bizarre behavior that happens at a division by 0. So that last limit doesn't exist. You don't have to worry about that too much, but I just wanted to point out that if your one-sided limits from the left and the right aren't equal to a real number and they don't share that in common, then of course your two-sided limit doesn't exist as well. Okay, so there's a recap of pretty much everything we've covered in this entire chapter 4, and we are now well into chapter 5 as we transition towards calculus.